Hi, everyone. So my name is Ellen Gao, and today in this session, we'll be building a self-regulating pressure relief mechanism in Go. But before that, I'm just going to talk a little more about myself. So my journey with Go started over 4 years ago at a company called Flybits. We're based in Toronto, Canada, and we're in the tech industry, obviously. I got the opportunity to attend GopherCon in 2022, which was also in Chicago. And that experience really showed me how great the Go community is, so I wanted to come back this year and share it with all of you. To give a little more background on the technical side of things, the pressure relief valves that we'll be building today is a simplified version of what I've implemented at Flybits last year. So the Flybits backend platform is made up of over 50 microservices that are written almost entirely in Go. These services communicate synchronously through gRPC and asynchronously through RabbitMQ and Kafka. And today we'll be focusing on the asynchronous part. You'll see why very soon. So here's the plan for this talk. First, we'll take a closer look at the problem we're trying to solve and what a successful solution looks like. Next, we'll familiarize ourselves with the code that we're working today, as well as the terminology that you will hear throughout this talk. And after that, we'll get into what I think is the fun part of the presentation, which is iterating on a solution. During this process, we'll leverage many tools in Go's standard library to improve our solution on every iteration. And finally, we'll discuss how the solution can be adapted to be used in real-world systems. So, what is the problem that we're trying to solve? Well, in today's world, software platforms are easily able to handle millions, if not billions, of requests per day. And as the platform grows, engineering teams tend to pour a lot more resources into their infrastructure. And why wouldn't they? It's a fantastic strategy. That is, until your team gets dragged into a cost optimization sink. But the balance between cost and performance has been an ongoing conversation in this industry for quite some time. As software platforms grow, it becomes increasingly important to make the most out of the resources that are being used. Platform growth is essential, but platform maturity can easily be overlooked. So today we'll be exploring how we can develop platform maturity through the lens of resource utilization. In real software systems, real resource utilization constantly fluctuates. And over time, when these fluctuations do stabilize a little bit, they often reveal patterns of utilization. Identifying these patterns are really key to finding what is normal for that system, because there's no one-size-fits-all. And healthy utilization makes the most out of its resources without getting too close to any resource limits. Something like what we see in this graph. But of course, things don't always go as planned, and this is where our problem surfaces. What do we do when our system encounters a load spike and we hit a resource limit? And in the bigger picture, during those high-pressure periods, how do we maximize throughput without sacrificing stability? If nothing is done, customers can experience degraded performance or even worse, service outages. And in a microservice architecture, these issues can cascade to other parts of the platform. Not fun. So what is the solution then? Can we just increase the resources? That's the obvious solution, right? Well, it depends. In situations where your platform is frequently unable to handle the operational load you have, this may be your best option. But if the load spikes are not frequent, the extra cost incurred to upgrade the system might actually cost you more than it's worth. And also, some resources, such as some databases, are not that easy to scale up. And doing so could lead to maintenance downtime and data migration. So if that's not our option, what do we do instead? Let's take another look at our problematic usage. but we'll specifically zoom in to one of the peaks. So far, we've been completely focused on total utilization, but maybe there's something more to it. Maybe it's time to look at the underlying processes that contribute to that total instead. You may notice here that all the underlying processes are negatively impacted as a result of reaching a resource limit. Now, all these processes can be important, but not all of them are probably equally urgent. And if you recall from the beginning of the presentation, I mentioned that we would be focusing on asynchronous communication, and this is why. Asynchronous processes are, by nature, not necessarily guaranteed to be handled immediately. And during high load periods, we can protect our system from reaching problematic usage by prioritizing critical tasks. And that is the basis of our pressure valve from today. So somewhere between our healthy usage and the hard resource limit, there's a soft limit. And that soft limit can signal the system to take action before we reach the actual limit. In other words, this is where we can detect that there might be a problem. Now that we've detected that the system is under too much pressure, we can respond to take steps to mitigate that issue. Specifically, we want to temporarily slow down the processing of non-critical processes. And that brings us from what you see here to this. By temporarily delaying work that is not immediately crucial to the system, we can prevent, hopefully, the total utilization from reaching the limit. And note that the messages that we're delaying are not dropped or lost, they're just processed later. Now, at some point, the total utilization should drop below the soft limit again. And when that happens, the last step is to recover normal operation by gradually ramping up those processes again. In other words, in this illustration, if process A is critical, but process B and C are not, then when we reach the soft limit that we've set, we should temporarily delay the processing of B and C, but leave A alone. Sounds good in theory, but how would it be applied in practice? Let's look at some code and build our solution together. If you'd like to follow along during the presentation or access the material afterwards, the repository is available for you here. Yes, that is a dog in the middle of the QR code. No, you cannot convince me that cats are better. So, let's go over some of the building blocks of our asynchronous communication system. It's good to point out here that this is not really a realistic representation of how things would work in a production setting, but for a demo, it's good enough. But regardless, let's go through them one by one. First, we have the producer. It's just a process that sends a message to a specific topic. It's not responsible for the actual message routing, only declaring where it should be routed to. For this demo, the producer pretty much just loops and publishes messages. And next, we have the queue. A queue is a first in, first out storage mechanism for messages, and each queue here is binded to a topic and a handler. The topic is used for message routing, and the handler is the function that is invoked for message processing. And here we see the queue configuration for two different topics, the topic and handler that I was just talking about. Now, under the hood, the queues that we're using are represented by buffered Go channels. I remember in the previous talk, I was told not to use channels, but here we are. In reality, these queues would be managed by an actual message broker, RabbitMQ or Kafka. And on the other side of the producer, we have the consumer. The consumer is just a process that accepts messages from a queue and invokes the handler. The implementation of the consumer is also quite simple. It receives messages over a Go channel and invokes the handler. Next, we have the messenger, which routes all the messages to the corresponding queue and exposes channels for consumers to accept messages. This is, again, a very much simplified version of something like RabbitMQ Kafka. I am not trying to build another one of those. So this is the implementation of our messenger. Whenever a producer publishes a message, the messenger just routes it to the right channel. Then we have the resource manager. It's responsible for keeping track of overall system utilization as messages are processed. And if it ever reaches 100, it'll just terminate the program. If resource alerts are enabled, which we'll talk about later, it'll also send alerts to consumers every time a resource threshold is crossed. The resource manager exposes a method to add a cost to the total utilization. And in some cases, as I mentioned in the previous slide, it will send alerts on the alert channel if the threshold is crossed. The remove function is the same idea, but it does the opposite thing. And we do have a lower threshold to be able to determine when it's safe to ramp up processing again. And lastly, we have the handler function. It's a function type that outlines the structure of the recipient's handling logic. The function is invoked by the consumer to deliver the message, and it's implemented, in this case, in our resource manager. Now, if you remember the queue setup, it was one of the fields that we actually provided. And if we take a closer look at the actual implementation, our implementation is quite simple. When a message comes in, it adds the cost of the message, waits for a little bit, and then removes it after some delay. And that's everything for the building blocks. So why don't we make things even more interesting? Because remember how I said there were 4 topics? This is the same setup as we've been discussing on the previous slides, just expanded to show all 4. I feel like they're quite self-explanatory, but in case you didn't realize, critical would be the most important, followed by priority, followed by normal, and last, and in this case least, low. So let's actually see this in action. In the first bare bones demo, what we want to see is fluctuations in the utilization. And we can understand the impact of the load spikes without any intervention. Messages on all topics are eventually negatively impacted by the load spike. So let's see it. Uh-oh, it only took 16 messages. So as we see, messages from all the topics have a cost to them and add up to a total cost for the system utilization. In this demo, I do generate some random load behind the scenes because adding randomness to your demo is always a good idea. But at the end of this, we do see what we were expecting, that the load has reached 100 and the program has exited, which is not really what we want. This I was supposed to show you before I did the demo, but I ended up explaining it to you. So this is a different screenshot of the same thing, just run a different time. And we need to change this. The program exited prematurely, and we reached the maximum utilization. All processes, including the really important ones that we said shouldn't get interrupted, did get interrupted. So let's see what we can do to change that. Before we can implement the throttling itself, we need to introduce an alerting mechanism. Essentially, our resource manager just needs a way to tell consumers when they should throttle. And since each consumer is doing work in a different Go routine, we need a way to send messages across Go routines. And luckily, Go has channels. So we take another look at the resource manager code that we were originally working with. After adding the cost of the message to the total utilization, we just check if it has crossed our soft limit, which in our case is set to 80. And if we have reached our soft limit, then we send the alerts to each consumer using the channel. The remove is the same idea, just on the other side of things. And for a consumer, we can add some kind of watcher to listen to these alerts and update the internal state to know when to throttle. In this case, it's just a for loop that receives values from the alert channel, and it updates a field in the consumer struct. All right, so now we get to iteration 1, which is actually implementing basic throttling. Here we want to expose configuration options for per queue throttling and update the consumer logic to actually apply the delay in between messages. For the queue, we can just add a flag to indicate which topic should be throttled. And from our list of 4 topics, let's just throttle the bottom 2. So we can see that the normal queue has throttling enabled, as well as the low queue. In the consumer logic, we'll do something straightforward. We'll be checking the current alert value and adding a fixed delay before invoking the handler, only if the alert is active. So if it's not active, normal behavior should happen. That being said, I should not have included so many demos, but in this demo, we want to look at the automatic detection of resource usage beyond its soft limit. Essentially, like what we said, critical and priority messages should be left alone. They should be processed as is. And normal and low messages should be processed at a slower rate when total usage is high and our alert is active. And in case you weren't paying attention the first time, this is how the output looks like. All right, if I clear this and then find my cursor, let's see how this goes. This one's a bit fast, but we'll scroll back. So in the beginning, we see that all the topics are getting consumed properly. And you can see the utilization fluctuating, but it's not really to a point that there's an issue for us. Eventually, we see that an alert has been triggered and we want to slow down. And there are some logs here that are showing that we're applying a delay on only low and normal. So again, priority and critical messages are processed as normal, but low and normal messages will have a delay. Now, at some point, the utilization should drop, and we should speed up again. And in our case, the priority and critical messages have all already been received, so all we're seeing over here are the delayed messages that we didn't process earlier. And with that, we've actually already implemented a basic throttler that prevents our utilization from getting to 100. This is the same thing that I showed, just highlighting some of the logs that you were seeing. So again, all the messages were successfully processed, critical messages and priority messages were unaffected, and normal and low messages were consumed at a slower rate when the alert was active. It does the job, but why stop here? On the next iteration, let's abstract this implementation using Go interfaces and implement 3 different throttling strategies. Because at the end of the day, the consumer shouldn't care how the throttling is done, just that it is getting done. So this is a throttler interface that we were talking about. For now, we only need one thing in there, and that is apply. And on the consumer, this is what we had before. We had a static wait But now, instead, we call apply. Now let's get into the 3 throttling strategies that we're going to implement. The first one is block throttling. It is the most aggressive strategy because when the alert is triggered, we want to completely stop processing messages. And when it is resolved again, we can slowly begin processing again. Interval is probably the most straightforward strategy to implement. When the alert is triggered, we add a static delay in between messages, and when it's resolved, we speed up, same as block throttling. Now, back-off throttling is probably the most interesting but also responsive strategy because when the alert is triggered, we start with an initial delay. If by some interval the alert has not gone away, we pull back even more and increase the delay. And when the alert is resolved, same thing as the other ones, slowly speed up and return to normal. So if you recall this diagram, we've just added the throttlers at the bottom before the handler is invoked. Now let's see how this translates into the code. We'll go ahead and implement the functionality to slow down message processing. In the block throttler, we want to stop message consumption completely. And from the Go language spec, if you have a select with nil channels, because communication can never proceed, it blocks forever. Do I recommend you put this to production? No. But we're going to use it anyways. So the interval throttler, we have actually already written the implementation for in the first iteration, because all we want is a fixed interval between messages. The only difference now is that we've moved the implementation to the throttler instead of in the consumer. And for implementing a back-off throttler, we want to start by applying that initial delay. Again, after some interval, if the alert has not been resolved, we increase the delay up to a maximum or up to infinity. That's your choice. But how do we actually do this? May I introduce you to an adjustable delay? An adjustable delay is just what I call a delay that is updated while consumers are receiving messages and throttling. Because of this, we have to update it in a separate Go routine, and as many of you know, that would require synchronization because apparently we don't like data races. So for the adjustable delay, we can see that there are 2 main things in the struct. The first is the actual delay, which is represented as a time duration. And the second one is a mutex, which is just for that synchronization that we talked about. In the actual adjustment, we pass in the interval, after which you want to increase the delay, the multiplier, which is just the factor that you want to increase the delay by, and the maximum delay. And to implement this, we can use something from the time package. Good old friend ticker. For a ticker, it does what we want by sending ticks on a channel at an interval. And because we want to adjust the delay on an interval, this does exactly what we want. So, in the for loop, we receive values on the ticker, and we update the value by multiplying multiplier with the proper conversions. Now, if the multiplier is greater than 1, don't worry about that for now, but if we've reached the maximum delay, then we have completed the work for the adjustment, so we can stop the ticker and return. When we pull that into the back-off throttler, the delay, the implementation of apply, is actually just like the interval throttler. Because the delay is getting adjusted in a separate Go routine, the implementation of the actual throttling ends up being the same. But then the next question is, how do we actually invoke this adjustment? Because the consumer gets the alert and it needs a way to know when to kick off or how to kick off the throttler delay adjustment when the alert is received. So let's revisit our interface. We can introduce a method that initializes any throttler values that we need. And for the implementation on the throttlers, for block throttling, there's really nothing to initialize. For interval throttling, all we're doing is setting the delay to the configured delay. And the backoff throttling, this is where we bring in the adjustment that we talked about. We start by setting the initial delay, and in a separate Go routine, we call the adjustment function to update the delay at an interval. Now, in addition to updating the current alert value, we need to initialize the throttler if one is configured, and this is just in our consumer watcher. For the queue, instead of just having a flag, we can give the actual throttler configuration with the values that we want. And it's not much of a change, but it will let us define what we need to apply the throttling. So let's see this one in action. For this demo, what we're expecting is to observe the impact of the 3 different strategies, how they're different, and if they're actually effective in working with each other. All right, let me clear this one again. And it's off. Oh, we already see it slowing down, and it has recovered. But if we come back here, when it starts slowing down, we see the different delays that were applied. Specifically, we see that interval stays the same throughout. Backoff eventually gets increased. And, well, after this one, we don't see any low messages when it's slowing down. But we notice that when we're speeding up, there's no ramping back up. And that's something that we do want. And it looks like because we just had a select with nil channels, our low consumer is stuck. You guys already know the format. And this is just another run of what I just described, where the interval delay stays the same and backoff increases. So for this demo, critical messages were unaffected. Priority messages just applied a fixed delay. Normal messages had the increasing delay. And low messages were not processed if the alert was active. So this is the second part of what we're trying to implement with throttling. Next up, which is iteration 3, is throttling with recovery. Now, we need to implement the recovery mechanism, and we can do that by using context cancellation. And this is where I'm actually very happy to tell you that we've actually done most of the groundwork for the recovery changes, and you'll see what I mean. From a previous slide, when we were implementing the actual backoff throttling, we summarized the implementation with this statement. We wanted to start with an initial delay. After an interval, if the alert has not been resolved, increase that delay. And there are some keywords here that if we take a closer look at the behavior that we wanted, we realize that backoff throttling and backoff recovery are really just 2 sides of the same coin. So to implement backoff recovery, all we need to do is start by applying some initial delay. After some interval, if alert has not been received again, decrease the delay down to a minimum, ideally in our case, 0. So we found that recovery uses the same mechanism as the backoff throttler in the previous iteration, which means that the actual implementation for the backoff throttler would be the easiest. Same thing as a throttler initialization, we need to expose the recovery initialization to the consumer. And let's go and implement them. So most things for the backoff recovery initialization looks the same, except that we're inverting our multiplier just to decrease the delay instead of increasing it. The interval setup is also kind of similar to what we just saw, But instead of having a fixed delay when you're throttling, we also need to start adjusting the delay when we're recovering. And the block throttler is along the same lines as well. But if you remember how we implemented the block throttler, how can we actually update the logic to go back and forth between throttling and recovery? Once we reach this piece of code for the first time, it seems like we're kind of stuck forever. It looks like a lot, but we'll go through it. But first, we need to separate the conditions that differentiate what should be done. In some cases, no throttling needs to be done. In some cases, we do want to throttle, and in other cases, we want to recover. So based on that, when we're throttling, we want to block until the alert is resolved. And I did mention context cancellation, and you can see that it's waiting for the context to be done. Now, every time the block throttler is used, the consumer can pass in this context. And when the consumer alert value changes, all it has to do is cancel a context to communicate to the throttler that you should stop throttling. On the other hand, when we're recovering, we just need to apply the delay. You'll notice this time it's done a little differently than before. In previous implementations, we would call time.sleep. But why is this different? Well, for this one, we only need a timer. It's a one-time event, and we wanted to listen to the context cancellation signal as well. If you think of the timer as kind of time.sleep, but with context cancellation, it fits with what we need. On the consumer, I've collapsed some of the code for easier reading, but when we receive a message, we just need to create a context with cancellation function. And when the alert is received on the channel, we call the cancel function. That context is passed into the throttler, and everything else is mostly unchanged. So let's see this one in action. For this iteration, we want to add the recovery. So the throttling response is the exact same as what we implemented in the last iteration, except for the block throttler. But the throttler should switch to recovery when the alert is resolved, and eventually the delays should go away when normal operation is restored. Again, if you forgot, this is the output. So let's clear this one more time and run our recovery. I know it doesn't seem like it's slowing down, but it is because it is printing extra logs, I promise. So in the beginning, we have the normal messages getting received on all 4 topics. When we slow down, we see that, again, same thing as last time, interval has that static delay, backoff is increasing, and we don't see low messages. But this time, when we speed back up, we start seeing low messages again, and we see that they do have delays applied to them. So in this case, the interval starts with 150, but yes, it should decrease every time. The same thing with block. And again, for this part, we ended up slowing down because we hit the threshold again. So we see the values increasing. And when it does recover, they should decrease. And they do. So you see that eventually in the recovery, we end up not having any delays getting applied because we don't need to. The alert has been resolved and our utilization is stable. And you see the low priority messages getting the least amount of love. And this is again just highlighting of what I just mentioned. And this one is the one for recovery. So a recap of this, what we saw was the same throttling behavior that we had in the previous iteration, but on the alert resolution, we slowly shorten the delay intervals until we restore normal operation. It's important to do this so that you don't overwhelm the system immediately again, because then you're just going to be in this nasty loop. So this is cool, But how do we adapt this to be used in real-world systems in your production code base? In the next few slides, I'm just going to describe some of the challenges that we faced at Flybits and the adaptations that we made to make it work. The first challenge is the throttling granularity. With us using RabbitMQ, it wasn't just based on topic, it was a topic and routing key. And in fact, each queue could hold messages from different routing keys. So essentially, you can have messages on the queue that should be throttled and other messages that shouldn't. We end up realizing that because of this, we can have multiple throttlers involved per topic as well. But let me paint a picture for you. What if we introduced a secondary queue and a consumer to process the throttled messages? And when the alert was active, the primary consumer just publishes the throttled messages to the secondary queue. The secondary consumer is then responsible for adding the delay before invoking the handler function. And when the alert is triggered, this is what I just said, the primary consumer publishes the secondary queue while delivering regular messages immediately. The secondary queue applies that delay and then invokes the handler function. And now when the alert is resolved, the primary consumer starts delivering all messages directly to the handler. This behavior may change if message order is important to you, but in our case, it wasn't that important. The secondary consumer applies the recovery delay that we worked with in iteration 3 before delivering the message. And there was a bonus advantage with this. I know a lot of people love HPA here, so let me tell you a story about HPA at Flybits and how we kind of shot ourselves in the foot before we introduced throttling. We had configured HPA to add some new pods if that service had queues with messages that exceeded a certain length. Makes sense, right? More work to do, more pods to do the work, everyone's happy, life is great, right? Well, I don't know if you can tell by the level of sarcasm in my voice that that was really not the case. It turns out, during the larger load spikes, the increased pressure on one of our databases ended up bringing the database CPU to 100. So requests would take longer to complete, and some of them were even timing out. That meant that the queues that were already backed up got even more backed up. And our lovely friend HPA did what it was told to do. It gave us even more pods to help narrow down the queue size. But with throttling, we were able to separate the HPA configurations for the primary and secondary queues, which meant that the queue length for primary queues would still trigger HPA, but secondary queue length would not. Now, the next challenge was usability. Ideally, with 50 plus microservices, we want to minimize developer overhead, but still give all devs the autonomy to decide how they want to throttle which messages. So what we did was package this pressure relief valve and provide easy access through a library. The backwards compatibility with the current message queue was maintained, but I'm not going to speak too much on that because you have to work at Flybits to find out. And the adaptation I mentioned was that we packaged all of them in an internal library, so all the services could use it. If you didn't want to add throttling to your service, there were no changes required. And the benefit of this is, as a developer, as a champion of the service, you have discretion to decide how you want to throttle what messages from what queue. And that is the benefit that we saw as opposed to using a managed solution. The next challenge is the alerting framework, because in today's demos, if you haven't noticed, the logic for the utilization calculation was quite one-dimensional. I mean, the message had a cost in it, and that's not really how it works in production. Plus, everything was co-located in one repository. In reality, metrics are often exposed through numerous sources in different formats. And even if you were able to access all of them, having every service monitor these metrics creates unnecessary overhead and complexity and maintenance. So what we did was build a custom monitoring service that ran in the cluster. The service periodically performed health checks, compared usage metrics of critical resources, like database CPU and memory and all that. And we were able to set the thresholds for each critical resource through config maps. That meant that we could have different thresholds for different environments, and it was easier to test for us. The monitoring service was responsible for actually publishing the alerts, and it did that through the asynchronous process that we used internally, which was RabbitMQ. And any backend service can just subscribe to the topic to receive those alerts. So overall, today, what we wanted to do was make sure we found a way to protect critical components of the platform from reaching resource limits in situations where scaling might not be feasible or just costly. So we built a pressure relief valve that automatically detects when critical components are at risk, responds to it, and recovers when it's appropriate. More specifically, we built 3 different iterations of this pressure relief valve. And the 3 types of throttling that we implemented, anything from basic throttling, where we just had a fixed delay, all the way to throttling with recovery, where we were working with context cancellation and timers. These are all tools that you have in your toolbox to do something like this. Finally, we discussed the adaptations of bringing this pressure relief valve to production code base. And on the way, had some fun with some of the Go tools, like channels, tickers, timers, and context. I'd like to give a huge thank you to everyone who has helped me along the way and supported me throughout this process, including the people who are listed here. And I had so much fun with this talk. I hope you did too. Thank you.